This video has been sponsored by Theorem. Good morning, fellow differential boys. You upgraded from being a fellow mathematician to a differential boy if you have watched this series up until now. If you haven't, you are still just a filthy fellow mathematician. That's still quite cool, I guess. Talking about Euler homogeneous differential equations today. You might have never heard of this type, but that thing right here is quite a powerful theorem, because with it you can solve all kinds of differential equations of that form, y prime equals to f of y over x. But what is this sneaky f that's right here in this theorem? Let's take a look at the conditions for this equivalence to hold. So suppose we have an interval, subset of the real numbers. We are going to call it j, and we have a continuous function f going from j to the real numbers. And we also have a pair of initial values, going to call them x0 and y0. And they are element of some open omega, which looks quite weird, to be honest. It's this weird looking set right here with all those conditions. But if you take a closer look, it's not that scary, because this set right here just includes information about x and y coordinates being element of the Cartesian product of real numbers and real numbers. You know what that is? That's the Cartesian product of j, which is a subset, and the real numbers. That's just a graph. So we just won't know where our information of x0 and y0 comes from. We have talked about this before a little bit. And if those little conditions hold, then the following two statements are equivalent. At least that's what the theorem states. We're going to prove it in a second. So suppose we have some phi or phi, whatever you want to call it, going from some I subset of the real numbers, but without zero, that's quite important, to the real numbers. And this thing is a solution to this differential equation I have talked about in the beginning. And also the solution satisfies those initial values, y of x0 equals to y0. And this statement is equivalent to a different statement. Suppose we have another solution psi going from the same interval I to the real numbers, and our psi is constructed that way. Psi of x equals to phi of x over x. You see, this phi of x is exactly this one right here. And that thing is a solution to this differential equation, which looks quite weird, to be honest. But like I said, it's a powerful theorem. And also the solution satisfies those initial values. Set of x0 equals to y0 x0, y0 over x0. And that's an equivalence, and what we really need to do to prove this statement, those statements, is that the first statement implies the second one, and then the second statement implies the third one. That's all we have to do. And we're going to do that now. Let's start off with the first implication. Both implications are quite straightforward. It's just basic calculations, to be honest. And we are going to solve an example in the end, so that you might see some applications of this theorem. So the first implication tells us that our starting condition is that our phi is a solution to this differential equation y prime equals to f of y over x, satisfying those initial values. And what we want to show, if this thing is indeed a solution, then that implies that psi is a solution to this differential equation, satisfying those initial values. The good thing is we know what our psi is, so why not? Maybe differentiate psi, because psi is the solution to this differential equation. So differentiating both sides and see what you get. So that's the first step to go. So that also means that psi prime is nothing but phi of x over x prime. And I hope it's self-explanatory that we are going to differentiate with respect to t. We can rewrite this a little bit. That is phi of x times x to the minus 1 differentiated with respect to t. X. Oh, I'm stupid. And now we just need to use the product rule. You could use the quotient rule, but that's just a special case of the product rule. So let's go ahead and do the product rule. So differentiating phi and multiplying this x to the minus 1. X to the minus 1 is just 1 over x. That's the way to go. And now we have the second part. So adding phi of x times the differential of x to the minus 1, differentiating that with respect to x. Differentiating that is quite easy. We need to drag the minus 1 down, and also we need to reduce the power by 1. So that's all there really is to it. So now we have phi prime over x, and then plus, and now we have a minus, just like I said, phi over x squared. And we came pretty far already, because if you take a closer look, we want to bring it into this form. So why not factor out a 1 over x and see what we get? So that also means that this is 1 over x times phi prime of x minus phi of x over x. We know everything about that right here, because the good thing is, by our starting condition, phi is a solution to this differential equation. So phi prime just evaluates to f of phi over x. So keep that in mind. And also we know what phi over x is. That is just psi. So let's plug this in. So we have 1 over x times f of phi over x minus psi. But what is phi over x? This is exactly just psi. So all in all, what we know is that psi prime evaluates to 1 over x times f of psi minus psi. And if you take a closer look, that's exactly what we wanted to show, because we brought this psi into that form, this psi prime into that form. Now we just need to show that those initial values hold. So what we can do, we can plug our x naught into psi and see what we get. So let's put it here. Psi of x naught is nothing but phi of x naught over x naught in that case. But what is phi of x naught? By our starting condition, phi of x naught is just phi naught. So that's quite nice. So we have phi naught over x naught. And that's exactly what we wanted to show. So that's that right here. And now we need to show the second implication. The second implication is even easier to show than the first one, to be honest. Let's dive right in. Our starting condition now is that psi is indeed a solution to this differential equation, satisfying those initial values, and psi is constructed like this, phi of x over x. And what we want to show, if this statement holds, then this implies that phi is indeed a solution to this differential equation, satisfying those initial values. The good thing is, once again, we know how our psi looks. So why not multiply both sides by x so that we can isolate our phi, and then we are differentiating both sides. And why can we multiply by x? Well, it's not equal to 0 because it's from the interval real numbers without 0. So that's quite nice. So that also means that phi is nothing but psi times x. Differentiating both sides leaves us with the product rule. So that's psi prime times x plus psi times x prime. But x differentiated with respect to x is just 1. That's cool. And our condition at the beginning states that psi is indeed a solution to this differential equation. So let's plug all the information in. So that's quite cool. So now we have 1 over x times f of psi minus psi times x, because we have this x right here, plus psi. This 1 over x and this x is going to evaluate to a 1. Then we have this minus psi cancelling out with this psi, and phi prime now is just f of psi. So that's cool. So that's equivalent to saying that phi prime is nothing but f of psi. But by our condition, psi is nothing but phi over x. So we end up with f of phi of x over x. That's what we wanted to show. And now we also need to show that our initial values hold by just, what are our initial values? Those are the initial values, so we want to show that this holds. So why not plug an x naught into our phi and see what we get? That also means that phi of x naught is nothing but, well, this is psi of x naught and also times x naught in this case. But what is psi of x naught? The good thing is that psi of x naught is nothing but phi naught over x naught. So there was our initial condition right here from this psi. So we have phi naught over x naught times x naught, which is going to evaluate to phi naught. That's exactly what we wanted to show. And now we are going to apply this little theorem to a differential equation, an ugly looking one. So let's apply this nice theorem. I hope you guys can see the connection between this differential equation and the theorem down here. So our theorem states that if we have this differential equation, an equivalence holds. And this right here is indeed a differential equation of that form. Y prime equals to this ugly bitch in the middle right here, but this is indeed just a function with respect to y over x, and also our initial values hold. And what our theorem basically states is that if we introduce a new substitution, this right here, we can also call it a set, for example, it doesn't matter, then this thing right here is indeed a solution to this differential equation, satisfying those initial values. Let's go through the process. So now, let some set be equal to y over x. This is going to satisfy the new initial values. And if we introduce this substitution, that means this differential equation is indeed equivalent to saying we have z prime equals to 1 over x times f of z minus z. That's all it really says. What is z? Z is just y over x. We are leaving it as it is. And, well, if we plug our z's in here, this is going to be z squared plus z plus 1 in this case. So that's our function f of z, f of y over x. So let's plug the information in. So we have 1 over x times, and now we have z squared plus z plus 1 minus z. This and that is going to cancel out, and it reduces to this little problem right here. So we have 1 over x times z squared plus 1. And now we are going through the basic procedure of solving differential equations, because this right here is quite easy to solve. We're going to divide both sides by z squared plus 1, not equal to 0, and then we are going to integrate both sides with respect to x, plugging in some initial values, and then we are basically done. And also you could make a change of variable, for example to t, so it doesn't look confusing. That also means that we have z prime over z squared plus 1 integrated with respect to x, and now our initial values from z naught to z. We are going to plug all the stuff in. And this is going to be equal to the integral going from x naught to x of 1 over x dx. This right here is just a name. You can also call it t, just like I said before, and it wouldn't change anything, so that you don't confuse yourself. The right hand side is going to evaluate to natural log of t, in this case, going from x naught to x, which is just the natural log of x naught of x minus the natural log of x naught. Okay, great. But what is the right hand side? You can interpret this z prime as dz over dx. And if you're a physicist, you could say that this 1 over dx and this dx is going to cancel out. If you do it a little bit more mathematically, the same thing is going to happen basically. So let's get rid of this stuff right here, and let's put a dz up here. And we have solved this right here before, link in the description probably. This is going to evaluate to the inverse tangent. So this boy right here is just the inverse tangent of z, going from z naught to z in this case. You can also make a change of variable once again, so that you don't confuse yourself. So this is just going to be the inverse tangent of z minus the inverse tangent of z naught. And this is indeed equal to this right here. But we are not done yet. Basically we are done. We have found a solution to this. But what we can do, we can resubstitute all the stuff back. So we can plug our z equals to y over x in and see what we get. So let's find out our general solution to this thing. So we can bring some stuff to the other side. So what do we have? We are going to leave this on this side. This is going to evaluate to the natural log of x over x naught in this case. I hope you can see where this comes from. Logarithm rules. Adding this on both sides and then using the tangent. So let's see. That means that z is now equal to the tangent of, and now we have the natural log of x over x naught plus the inverse tangent of z naught in that case. And just like I said before, you can resubstitute this y over x into here. So we have y over x is now equal to this chunk, and z naught is nothing but our new initial values, y naught over x naught. So this is now y naught over x naught. And all there's really left to do is to multiply both sides by x, not equal to 0. That means our general solution to our original differential equation is x times the tangent of this argument. And then we are done. So that might look kind of confusing, but this theorem is quite powerful. If you did enjoy this video, please like and subscribe and recommend me if you like. If you want to support me a bit more, link to my Patreon is in the description. I'm doing all the stuff for free, so I would highly appreciate some support from you guys. And up until the next video, have a differentiated day, I guess. See ya.
Oh nein.
Oh, ernsthaft? Oh.